Today we're going to talk about matter. As you might already know, matter is anything that has mass and takes up space. Why do we talk about matter? Matter is important in many different aspects of chemistry. For instance, if you're learning about physical properties such as density, you might want to understand why one substance like helium is less dense than another substance like lead. We're learning about chemical properties in our future. You might want to know when a chemical reaction occurs, what's actually happening with the atoms and the molecules as they rearrange themselves. In science, there's a big question looming out there. What is all matter made of? In other words, what's the smallest particle that makes up everything we know of? To understand these questions, we need to know a little bit more about the basic building blocks of matter. So let's talk about what can things be made of. There are two basic types of particles that can make up matter. The first is called an atom. You've probably heard of an atom before. An atom is the smallest particle possessing the properties of an element. Notice I didn't say it's the smallest particle there is. I'm sure you've heard of smaller things like protons and neutrons and even electrons. Maybe your knowledge of chemistry and physics goes farther and you've even heard of things like mesons and bosons and quarks. When we talk about the atom is the smallest particle that retains the properties of an element. For instance, if I were to find an atom of carbon in Chicago versus an atom of carbon in California, they would act exactly the same way. Scientifically, how do we represent an atom in chemistry? You can draw just a circle. Now we know it doesn't look like this in real life. But when we try to think of things with our molecular eyes, when we try to look at things closer than even a microscope could, it's important in chemistry to try to visualize things with your chemical eyes. You have to try to predict what's going on a molecular level. So, when we talk about atoms in chemistry class, I want you to visualize a small round circle. As we go through some of these definitions, you'll notice I throw out analogies that try to help you relate these things to your real life. When I talk about something like an atom, I'd like you to visualize perhaps a Lego piece. Notice it's a small, tiny piece that can be used to build larger things. Another picture that might remind you of what an atom is a brick. Imagine one small brick. Of course, if you took many bricks, you could make something larger than that. The next type of building block that we're going to talk about is a molecule. There are some substances where the basic unit is a molecule, not a single atom. So what's the difference between the two? A molecule is a chemically bonded group of atoms that acts as a single unit. If we were to draw a picture of what this might look like on a molecular level, you could draw many different options. We might take a yellow atom and chemically bond it to a blue atom. Now when I say the phrase chemical bond, that means that these two atoms are linked together and it requires energy to pull them apart. Let's throw out a few more examples for you. What if I were to take a pink atom and chemically bond it to another pink atom? Again, this is a molecule. You have to have at least two atoms and they're chemically bonded together. Let's get a little bit crazier now. What if I were to take a blue atom and connect it to three red atoms? Again, this is an example of a molecule. We have at least two atoms and they're chemically bonded together. Now that you understand the basic building blocks of matter, let's talk about what we can make out of atoms and molecules. The first thing that we can make is called an element. I'm sure you've heard about an element before, but what does it mean to be an element? The definition for an element is a substance composed of one type of atom. So to represent that, we're going to use, let's say, these yellow atoms. Notice that every single atom is identical. I'm sure that you're aware of a lot of different elements out there. An example would be gold. How about carbon? basic things like copper or zinc. How about something crazy like helium gas? All of these are examples of elements. I want you to notice that the atoms are single. They're by themselves. We call this a monatomic element. Think about the prefix. Mono means one, or single. Single atoms. But the same atom must be repeated again and again. To show that, we're using yellow, 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 all yellow atoms. There's another type of element that's important to be aware of. It's called a diatomic element. Let's think about that definition. Di means two atoms. In this type of element, we have two atoms that are chemically bonded together. They exist as a single unit that travels around together. Notice in this type of element, we're still using only one color. Every atom is identical to the next atom. We've got pink, 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 all pink. How do we know which elements are monatomic versus diatomic? I like to use the acronym Hankelbrief to help remember the different elements that are diatomic. Let's go through them right now. The H stands for hydrogen. When you encounter the element hydrogen, the atoms are always connected. There are two of them connected together, and they travel around as a single unit. The second element is oxygen. Oxygen gas that we breathe in. The two atoms are always connected together. N stands for nitrogen. N2. Nitrogen is also in the air that we breathe. In fact, it makes up about 79% of the air that your lungs take in. Cl stands for chlorine, a toxic green gas. The Br stands for bromine, which is a red liquid. I is iodine, a purple solid, and F stands for fluorine, which is a yellow toxic gas. So these 7 elements, whenever they're found in nature, do not exist as single atoms by themselves. They exist as molecules. The two atoms are connected together with a bond. So we've got monatomic and diatomic. So let's give you a few analogies. What do we want to visualize from our real life that can help us remember the difference between these two things? When I think of a monatomic element, single atoms, I like to think about Cheerios cereal. Every single little Cheerio looks exactly like the next one. When I think about diatomic atoms, this one's a little bit harder, but I want you to envision 2 cherries with their stems still attached. They look exactly the same as each other, but there is a bond between the two. Let's go on to another type of matter, a compound. And how is it different from what we've already learned about with an element? A compound is defined as a substance composed of 2 or more elements linked by chemical bonds. So there's the key to this definition. You've got to have at least 2 different elements that are linked together. So how would we represent that with our little colored atoms on the board? Well, we could take a blue atom, and perhaps we might link it to a red atom. Okay, so we're going to repeat this over and over and over again. Okay, so with this compound, we've got 2 different atoms. One of them is the red atom, which has its own properties. And then there's the blue atom, which has its own properties. So there's 2 different elements that are linked by a chemical bond. Now notice, this molecule is shown again and again and again. You'll also notice that within a compound, the ratio of elements is constant. Always one blue attached to one red. If we were going to give another example for you, we might do something like, how about a red atom with two yellows attached? Keep in mind, we have to show the same molecule again and again. It's a fixed ratio of elements. So let's do another molecule of that. Again, we've got one red, two yellows attached. So these are two different examples of a compound for us. So what could I think of that would help you relate this to your own life? My best example, I think, for a compound would be an Oreo cookie. Think about an Oreo cookie. You've got the dark cookie on the top, the dark cookie on the bottom, and you've got the white creamy filling in the middle. Two very different things, but remember, it's always in the same ratio. Always the two cookies, always the one white filling in the middle. Let's go on to our next definition. It's a mixture. How is a mixture different from an element or a compound? It's very easy to distinguish a mixture from an element and a compound, and here's what you want to focus on. Two or more substances physically combined together. So we've got to have two different things, and when I say physically, I mean let's mix them up together. How would I draw an example of this on the board with our atoms? Okay, well, how about if I had a yellow diatomic molecule in there, and a pink atom, and perhaps a red atom, and now let's throw something crazy in there. How about a blue and a yellow? This is a mixture of different types of things. You could have two things, you could have four things, you could have seven things. I'm going to give you an example from my own childhood. When I grew up, we didn't have camps every single day or soccer practice to go to every single day. We spent a lot of time outside playing with our friends. Well, one of my favorite things to do was to make goulash. No, not the real German goulash with noodles and mushrooms and chicken. This was goulash from the outdoors. I would take a bucket, I would fill it with water, I'd throw some dirt in there. I found these little tiny red berries, maybe a couple of twigs, throw some leaves in there and a stick, and I would stir the entire thing up. And I would call it goulash. Now here's the important part. If I wanted to separate all of those different things that I had put in that bucket, let's think about it. I actually could, just by using my hands. I could reach in and I could pick out the red berries. I could reach in the bucket and I could take out the twigs. I could take out each individual thing and create those piles again. Now you might be saying, well, what about that handful of dirt that you threw in there? Well, I would argue if I let the bucket of dirt and water sit for many, many days, eventually that water would evaporate off and we'd just be left with dirt. You see, if you can physically put all these things together, you can physically take them apart. The same thing is not true about an element and a compound. These different molecules that we have within a compound, you cannot pull them apart easily. You would have to put energy in within a chemical reaction in order to take the yellow atom away from the red atom, or to separate the red atom from the blue atom. We would have to use chemical means, chemical reactions to actually separate those things. So when you focus on how do I know what a mixture is, think about physically mixing this together and you can physically take the things apart.
We're going to use this pyramid to help us classify matter. From the top, we'll begin in a very general sense, and as we move toward the bottom, we become more specific. So what is matter? Matter can be described as anything with mass and taking up space. What are some examples of this? Solids. Solids are materials that have atoms that are very close together. Of course they have mass and take up space. Liquids have atoms and molecules that might be a little bit looser yet still touching. Again, it qualifies as matter, anything with mass and taking up space. And even gases, which have the atoms or molecules quite a bit of a distance apart, they're still matter. It seems like everything is matter, but not quite. The one thing that does not qualify as matter is energy. Matter can be broken down into two categories. There are pure substances, and there are other things that are not pure. So what's the difference between the two types of matter? If it's a pure substance, we're looking at a material that has a constant composition. We're going to see the same thing throughout the entire material. When substances are pure, they have definite melting points and boiling points. These are physical properties that do not change. Because the substance is consistent throughout, we can identify the substance by its melting point and boiling point. On the other hand, there are substances that are not pure. Mixtures would qualify as substances that are not pure. Remember, mixtures have several things that are physically mixed together. When you have things that are physically mixed together, the melting point and the boiling points can vary. In other words, they're not always consistent. They can easily change depending on the ratio of components in the material. Let's look at this idea a little bit further. If we were talking about the metal zinc, zinc always has a melting point of 419.5 degrees Celsius, and the boiling point is always 907 degrees Celsius. The only time that those numbers would vary is if the atmospheric pressure were to vary or change. In other words, unless you're in the mountains of Denver, Colorado, these melting points and boiling points will always be consistent. On the other hand, I want you to think about taking a cup of water and adding just a little bit of salt to it. When you try to boil the water will boil at 103 degrees Celsius, which is just a little bit higher than water's normal boiling point of 100 degrees Celsius. But now let's change the ratio of water to salt. If I take that same glass of water and now I add lots and lots and lots of salt to it, I make a very concentrated salt water solution, I can actually cause the boiling point to raise even higher. So instead of maybe 103 degrees, we could get a boiling point of 105 degrees Celsius. So you see, the fact that we have a mixture means that we don't always have a consistent boiling point. It's not always going to be the same number. It really depends on how much of each component we put in the mixture. We can go back and look at pure substances, and we can actually classify them down a little bit more specifically. In chemistry, there are two types of pure substances. First would be an element. To determine the elements, you can look on the periodic table. Let's talk about just a few of them. One element that you might be familiar with is carbon. In this example, we have charcoal, which is used in fish tank filters. Another example of an element is one that we see all the time in jewelry. That would be gold. A third element is one that you might be familiar with. It used to be used in thermometers. It's mercury. All three of these elements are considered pure substances. Another example of a pure substance would be a compound. Let's talk about some examples of a compound. If you remember the difference between an element and a compound, an element is composed of one type of atom. A compound has at least two types of atoms that are chemically combined. In this example, we see sugar. Notice in the formula that we have a definite ratio of 12 carbons and 22 hydrogens and 11 oxygens. Sugar has a definite melting point and boiling point that will not change. One more example that I know you're familiar with is water, or H2O. Water always boils at 100 degrees Celsius if it's pure, and we're at normal atmospheric conditions, and water will also freeze at 0 degrees Celsius. You'll notice that there are two empty categories under the not pure heading. We need to fill those in. There are two types of substances that are not pure. One of them is called a homogeneous mixture, and the other a heterogeneous mixture. Those are some fancy words, so let's throw out some definitions for you. The word homogeneous means the same throughout, or uniform. As you look at this substance, it might not look like a mixture to you. It's going to look consistent throughout, but we've really got at least two substances that have been physically combined together. A good example of a homogeneous mixture would be Kool-Aid. Imagine taking a glass of water and adding some cherry Kool-Aid to it. As we stir it up, all of the Kool-Aid particles dissolve and we end up with a red solution. Because it looks the same throughout, we call this a homogeneous mixture. A heterogeneous mixture is something that is different throughout. As you look at one part of the mixture and compare it to another part, they're not going to look consistent. They're going to look different than each other. A great example of this would be Italian salad dressing. If you're going to pour some Italian salad dressing on your salad, when you first get the bottle out, you might notice that the oil has formed a layer on the top of the bottle, and the vinegar has formed a layer on the bottom. Of course, there's little bits of spices and garlic and other things that are in there. When you use Italian salad dressing, you shake it up in order to try and make it consistent. But you'll notice if you let it sit there long enough, it will return to the two layers of oil and vinegar just like it was in the beginning. Let's look at mixtures a little bit more closely. There's actually two types of homogeneous mixtures. One of them is a solution, which we've already mentioned. A solution can be defined by the size of the particles that you see. We already had mentioned that it looks the same throughout. The particles in a solution are extremely small. These are things like atoms and molecules, and they're too small to be seen by the human eye. Some great examples of solutions would be things like salt water, which we already mentioned, soda pop, something that has carbonation or carbon dioxide dissolved in it, as well as sugar and flavoring. Air is even a solution. It's a combination of nitrogen gas and oxygen gas and very small amounts of other gas, but it's uniformly mixed. Alloys are solutions. Imagine making brass in which you take copper as the major component and you dissolve zinc into it. On the bottom is a visual of a glass of water with salt being dissolved into it. Once the salt has been dissolved, we can no longer see it because the salt particles are so tiny we can't see them with our eyes. Another type of homogeneous mixture is a colloid. A colloid is a little bit different than a solution because the particles within it are medium sized. They're a little bit bigger. And because of that, they do something unusual. If you were to shine a light into the liquid that's inside of a colloid, you would actually see the light reflecting off of those medium-sized particles. Imagine driving down the road at night and it's very foggy. Your headlights will project a beam of light. They hit the fog and they reflect off. This is what the Tyndall effect looks like. Some good examples of colloids for you are milk, fog, like we said, Jell-O is a colloid, mayonnaise, and also smoke. Down on the bottom you can see a picture of a colloid, and you'll notice that as the light is shining through it, the particles are large enough that they reflect the light. And the line that you're seeing is what we call the Tyndall effect. There's one more type of mixture that we need to talk about, and that's a heterogeneous mixture. It's also called a suspension. And it can be defined as something that contains large enough particles that you can actually see with your eyes. Some good examples of this would be sand in water. And in a case of a suspension, you'll notice in all of these that there's different phases here. In other words, the sand is going to sink to the bottom, and that's going to look very different than the water that's on top. If you don't know a lot about concrete, it involves four main ingredients. You've got cement, which is the glue that holds everything together. You've got water. Then you've got fine aggregates, which is something like sand, very small particles. And then there's large aggregate, which is rocks. If you were to crack open a piece of concrete, it would look very different throughout. And the final example is oil and water, which we mentioned. Oil is going to form a layer on top of the water, and they will not mix. It's not going to look the same throughout. On the bottom, we can see an example that shows that for you. So now that we've defined some very specific things about matter, why don't we do a little bit of practice? Let's do 3 examples. Here's our first example. Take a look at the sample that's shown on the screen. I'm going to ask you a few questions about it. I want you to try to write down the answer and commit to it, not just wait until the answer is shown. So here comes your first question. Take a look at this substance that I've shown you. And feel free to use your definitions that we just talked about. Would you say that this is a pure substance, or is this a mixture? To answer this question, you should be asking yourself something. As I look at the particles, does each particle look the same? I would say yes. In every single case, you'll notice there's a red atom that is attached to 3 green atoms. For this reason, this is a pure substance. Our next question, if this is a pure substance, that means it can only be one of 2 things. Are we looking at an element, or are we looking at a compound? Take a moment and think about that and try to commit to an answer. You should be asking yourself, do I see one type of atom? In other words, is every single atom in this box look identical to the next? An example of that might be all green atoms or all red atoms. I don't see that happening here. I do see the same particle repeated again and again, but within each particle I definitely see 2 different types of atoms chemically bonded together. That is the definition of a compound. The third question asks you, the little particles that you're looking at, are these things atoms or are they molecules? You should recall that atoms are single individual building blocks. A molecule would be when you have at least 2 atoms that are chemically bonded together. So as you look at this sample, you should be saying to yourself, these things are definitely molecules. A final question for you on this example. Which of these formulas best matches what you see in the circle? Here are 3 options. I want you to take a look at them, and let's see if we can narrow it down and figure out which of these formulas is probably the right one. Well, as I look at the first option, 4R, I guess that probably means 4 red atoms. And then it looks like we're adding 12G, which I guess means 12 green atoms. But the way that this is written is suggesting that this is a mixture, that the red atoms are physically being mixed together with the green atoms. And I would argue that this is not a physical mixture of atoms, it's actually chemical bonding that's going on. When you see an atom placed next to another atom and they're touching, we're suggesting that that thing is actually bonded together. So I don't see 4 individual reds and 12 individual greens, so I'm going to get rid of my first option. Look at the second option, R4G12. Because I've written the subscripts in that way, the R4 means that we've got molecules here that have 4 red atoms within it. In every single particle, do you see 4 red atoms? And do you see 12 green atoms? No, that's not the case. We don't have one huge molecule with 4 reds and 12 greens. So the second option is out. Well, that leaves us with the third option. Let's talk about why this is the best formula. You'll notice there's a big 4 in front. The big 4 is representing the fact that there are 4 particles shown. In every single particle, there is 1 red and there are 3 green. That's where we came up with RG3. 1 red, 3 green. And that same particle is repeated 4 times. Here's our second example. Ask yourself, is this a pure substance or is this a mixture? As I'm looking at this sample, I don't see the same particle repeated again and again. Instead, I see some that are black squares and some that are orange triangles. And it looks like they're kind of all being physically thrown together. That's why this is a mixture of things. As you're looking at the sample, do you think that these are individual atoms that you're looking at? Are they representing molecules, or do you see both of those things shown? In this sample, I don't see 2 squares touching each other, or 2 triangles touching each other, or even a square touching a triangle, which means I can rule out the option of molecules being here. We do not have 2 or more atoms chemically bonded together. They're all separated from each other. The things that we're looking at here are all individual atoms. One final question for you on this sample. What formula do you think matches? Well, the first answer, I'd say this is kind of a smelly answer, 4BO. Does 4BO describe what you're looking at? For this to be 4BO, we'd have to see 4 particles shown, and every single particle would have a black square attached to an orange triangle. I'm going to say that that is not happening. Goodbye, smelly option number 1. In the second option, we see 3 orange added to 4 black. That's not a bad idea here. It does look like I have 3 orange triangles, and it does look like I have 4 black squares, and they're all physically blended together rather than being bonded. It looks like number 2 is a pretty good option. So what about number 3? What could possibly be wrong with this? When we write B4O3, the subscripts are suggesting that we have 1 particle that has 4 black squares in it, as well as 3 orange triangles in it. This is not one huge particle. In this sample, we have 7 things that are spread out. None of these are touching each other. This is a physical mixture. This is not a compound that we're looking at. So the best option is going to be the second option. Okay, this is our final example. Would you say this is a pure substance, or is this a mixture of things? I'm hoping you're noticing that the same particle is repeated again and again and again and again. This is the same thing being shown over and over. We don't have a particle in there that looks different from everything else. This is a pure substance. As you look at the sample, look at the individual particles. Would you say that these things are individual atoms, or would you say that they're molecules? Because there's 2 atoms that are chemically bonded to each other, we would have to say that these are molecules that we're looking at. Is this an element or is it a compound? The one thing I notice about this sample is I see blue, all blue. Blue, 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 over and over and over again. And I want you to remember the definition of an element. An element is a substance composed of one type of atom. This is one type of atom. This is an element. Our next question brings up some vocabulary. There are 2 types of elements. Would this be described as a monatomic element, or a diatomic element. And you have two atoms that are exactly the same that are attached to each other by a chemical bond. That's what we're looking at here. This is a diatomic molecule of an element. Final question, which formula matches the sample best? The one that stands out very quickly to me as being wrong is the middle one, 8B. That means 8 blue atoms, all separated, suggesting it's just a whole bunch of atoms that are not bonded together or not touching at all. I'm definitely going to rule out that option. How about the last option on there? That 2B4. The 2 that you see in front means that there's 2 particles. Well, I don't even see 2 particles here. And I certainly don't see 2 particles that have 4 blue atoms all attached together. So I'm going to say that that last option also doesn't work. So how about the first one? Are there 4 particles shown? Definitely. Within each particle, do you see 2 blue atoms chemically bonded to each other? Absolutely. The correct formula is 4B2.